Welcome all of you. We'll start our session in 1 to 2 minutes. So before I start the session. So I would like to open the session for the question and answer. So if you have any doubt regarding this course or whatever the topic covered in this course, so you can ask that me, and we will discuss that one. You can unmute it yourself and or to ask the question. Or you can also use the chat box to put your question or any doubt. Okay, welcome all of you. So this is our seventh session on these seventh interactive session on the course study guide in the organic retrosynthesis, a problem solving approach. And in this course, as we are already discussing from the last few weeks, we are dealing with the different retrosynthesis different approaches used in the retrosynthesis, and we have already covered several concepts in this retrosynthesis, mainly the the introductory session that we have already discussed, like different terminologies and all, and also retrosynthetic disconnection. For the different molecule, we have covered almost more than 50 molecules as of now. And again, in this synthesis, we have already discussed the regioselectivity, selective reaction, regioselective, as well as the chemoselective reactions. And in the last video, I have covered like different oxidizing and reducing agent and their how they selectively do the oxidation and reduction of the different functional group. So that part we have already covered. Right now, we are slowly moving toward the some stereochemical aspects in the this uh, retrosynthesis, and we are starting. We have already uh, covered many problems on the retrosynthesis which do not involve the stereochemistry. But from this session onward, we are gonna cover some of the problems which involve the stereochemistry. So before going to directly the problems, I will in this video I will cover some concepts on the stereoselectivity in the organic synthesis, and we start from the very basic, and slowly we'll move to the some advanced concepts of this stereoselective synthesis and the retrosynthesis, which involve the chiral centers. Okay, so before moving to the session, so I would like to ask you if you guys have any doubt regarding the topic that we have covered up to this week 7. So you can ask the question now. So the session is open for the question and answer. So I will, if you don't have any question, I will move to the actual the topic that I have taken for today's discussion. So which is the stereoselectivity in the organic molecule. So as we have already covered regioselectivity. So how the regioselectivity is? The regioselectivity means the difference between the two sites and the reactivity of, let's say, reagent toward the particular site. So that governed by the regioselectivity. So let's say you are doing the oxidation of the two systems in which we have the primary alcohol and the secondary alcohol, and we perform the oxidation reaction. And in that oxidation reaction, let's say the only one particular alcohol get oxidized. So that will we call it as a. So let's say if we have the So this alcohol and let's say this alcohol. So in this case, there are these two are both are the secondary alcohol. But if you look at here, it has the adjacent this double bond. And because of this, let's say if you perform the reaction in presence of the MnO2, so this oxidation reaction occurs. In this case, the oxidation of this alcohol occur preferably, and this alcohol, which is the isolated one, which shows doesn't show reactivity in this MnO2. So this we call as a chemoselectivity. See, only one functional group selectively react. So this is chemoselectivity. In the radioselectivity, let's say we have already studied several example, which has let's say so addition of the HBr across this double bond. So the so Br attached here and hydrogen attached here like this, right? So that we have seen already. So like this. So the bromine in this case particularly shows addition at the terminal position, and so there is preferential reactivity of this HBr. So bromine shows addition at the terminal position here. So that mainly the radioselectivity. This concept we have already covered. Now we are gonna move to the stereoselectivity. So what is this stereospecific reaction? So it is a reaction where mechanism means the stereochemistry of the starting material determines the stereochemistry of the product. And there is obviously uh, no other choice means let's say if you have the example of SN2 reaction. So let's take this example of this SN2 reaction. Here in this SN2 reaction, you can see so you have this iodine and you treat with this with the NaOH. So now the OH minus is the, we have the nucleophile. So this OH minus shows attack on the opposite side. So this OH negative attacks on this carbonyl center and this iodine get eliminated. Now if you look at the stereochemistry of the final product, which is exactly opposite to the starting one. So this is basically a example of stereo-specific reaction. So in which there is no other choice in this reaction. We got exactly, this is the only product we got, which is nearly 100%. So that's why I mentioned here, there is no choice in this reaction because we are getting exactly about 100% yield of this final product, right? So this is like example of stereo-specific reaction. So in this reaction, the term specific if in such reaction the starting material differ only in their configuration and converted to stereospecifically distinct product. According to this definition, stereospecific process is necessarily stereoselective, but regioselectivity does not necessarily imply stereoselectivity. So earlier I have shown the example of regioselectivity. So the stereoselectivity is different from the regioselectivity. And sorry, the stereoselectivity does not necessarily mean stereospecificity. So here in this case, you can see, so there is again inside the specific reaction, there is two terminology only differentiate between stereoselectivity and stereospecificity. So selectivity means something getting measured, but stereospecific means it is getting 100%. There is no other choice. So that's the stereospecific. So in the SN2 reaction, this reaction is example of stereospecific reaction, right? So you can see, so this SN2 reaction, which is a stereospecific reaction. Always inversion in compression we get in this reaction. Now, if you look at the example, another example. So here is the another example in which you can see, uh, this is the elimination reaction, E2 elimination reaction. So why this E2 or SN2, that 2 stands for? It is biomolecular reaction in which this reagent and the starting material both are involved in the rate determining steps. So that's why it is called as here the E2 elimination or the sorry, SN2 elimination and SN2 substitution, and this E2 is mainly because the reagent NaOH, this O negative, is abstract this proton, and parallelly this proton, the electron involved in the bond formation, uh, carbon hydrogen bond formation, move to the formation of double bond, and this Br negative get eliminated. So this is the example in which you can see both molecules are involved. So this is therefore it is called as a E2 elimination. Okay. Anyway, we come to our concept. So stereo specificity. So in this case, we are getting this Z product as a major product, and therefore this reaction is called as a stereo specific reaction. So you keep remember these two examples. These are the examples of stereo specific reaction or the stereo specificity. But what about the stereo selectivity? So let's say we'll take some example of stereo selectivity now, or we'll cover this first, the stereo specific examples first, and then we'll move to the stereo selective some examples. So this is another example of stereo specific reaction in which you can see. So this is the example that shall earlier also shown, which is the E2 elimination reaction. This proton abstracted by the this base NaOH, and the Br negative get eliminated. So we get the Z product as a major product. So therefore, this gives the Z product. But we have the another configuration in which instead of this Br negative directing upward, if this Br negative directing downward, so now what happen? So we get the exactly opposite product, which is the E product in this case. And so this the product formation with the stereochemistry in the product is mainly directly depend upon the stereochemistry from in the starting material and in these stereospecific reactions. So if you look at the reaction mechanism here for both of these reaction, you can clearly see here. So in this case, for this kind of E2 elimination, we need to have this the proton and the eliminating or the leaving group anti to each other. So if you look at this conformation, you can clearly see this hydrogen which is directing downward and the Br directing upward. In this conformation, they are anti-periplanar to each other. And in this elimination, you can see the proton abstraction takes place followed by the Br elimination. So therefore, this is the this leads to the formation of this Z product, and the opposite happens in this in which the Br directing downward. So these are the stereo specific reactions. Now let's take the example this already discussed, the SN2 elimination. So if you have the any nucleophile and leaving group, so nucleophile attack exactly opposite side to the leaving group, and we get the inverted in the comparison of the product, right? And let's take the another some examples. So this take this example of this CHBr2 Br3 and the influence of the third butoxide. So what it produce? So if you look at this structure of this reagent, CH, Br, Br, and this another Br. So in presence of this strong base, here the potassium third butoxide, it abstracts this proton, and we get this cation here on the carbon, followed by the 3 bromine, 1, 2, and the 3. So this Br negative get eliminated, we get the carbene intermediate. So this carbene is looks like this. So this carbene intermediate attacks, uh, get attacked by this olefin. So this olefin, when it react with this carbene, we get the formation of this product in which this cyclopropane ring get formed. And if you look closely, so in this case, the stereochemistry of this methyl, they were seen to each other. Now in the product also, they are uh, on the same side to each other. So that will be remain constant in the product. But if you have the starting in which these methyls, let's say, upon trans to each other, now in the product also we are getting accordingly the stereochemistry trans to each other. So that's why here this reaction is also the example of stereospecific reaction. Another similar example, if we use the MCPBA, or that is metachloroperbenzoic acid, or any H2O2 on the olefin, so we get the formation of the epoxide, and in the same this epoxide formation also is the example of stereospecific reaction. Now let's move to the stereoselective reaction. Do you guys have any doubt up to here in the stereospecific reaction? I can elaborate more if you have any doubt, or I will directly move to the further point, the stereo selective reaction. Now, as of now, we have seen stereo specific reaction in which we are getting 100% product according to the whatever the starting material, stereochemistry in the starting material that we have. But here we are not getting 100%, but it is kind of selective. So let's say a reaction where one stereoisomer product is formed preferentially over another. The mechanism does not prevent the formation of two or more stereoisomer, but one of the product is predominant. That is, we are getting one major product, and maybe there are some minor products. So these are called the stereoselective reactions. And selectivity, this is the preferential formation of one stereoisomer over another in a chemical reaction if the stereoisomer are enantiomers. We'll speak about enantiomer selectivity, that is quantified by enantiomeric excess. So what is this enantiomeric excess? So that will also I will cover. So just remind me, I will discuss this enantiomeric excess as well as diastereomeric excess also in the later part of this video. So if the diastereomer, one speak, that will be diastereoselectivity. So let's take the example of this selectivity, stereoselectivity. So this is the epoxidation reaction, and if they perform epoxidation reaction in presence of the metachloroperbenzoic acid, so on the trans, there will be two product formation. That is, let's say this two product formation takes place. So which is like a 50-50%. There are possibility of formation of these both of this product. So this is kind of example of this stereoselectivity. In the sharp place epoxidation also, you can see there are one product for only 20% and another product from 98%. And in this case, since we are doing the minus diethyl tartarate, so it in the mechanism it shows the one product formation preferential over another. So this is example of stereoselectivity. And further, if you look at the another example, and in which you can see the reduction of this bond. So in this palladium reduction, what happens? So this palladium substrate, this double bond, and the hydrogens attached on the palladium. So this hydrogen addition takes place on this double bond on the syn side. So on the syn side, first this complex form. So this is basically this downward is this is the entirely this palladium surface, and on the palladium surface, this hydrogen get initially attached in this manner, and then on these olefin, it forms partial bond and followed by the complete bond formation. But in this case, if you look at the mechanism, this addition of the hydrogen takes place on the syn side. But if you look at the starting, it has the bulky methyl group. So the sterical crowding will be there. And therefore, with attaching these two hydrogens will be comes from the downside, right? So that's why this product get the major form and another product will be minor. And this is example of the diastereoselectivity. So any doubt up to here? So if you have any doubt in the stereo specific reaction or the stereo selective reaction, please let me know. Okay. So we'll move to the some more example of this stereo selective reaction. So please observe carefully in this reaction. In these few examples, you can clearly see. So this is the first example of the epoxidation of these structure, and you can see. So in the upward, there is a steric hindrance of this CH2 group, and when it is happening, this epoxidation, where this epoxidation happen along with these steric hindrance, we also cannot ignore this has the some concave structures. So basically, if you look at the plane of this molecule, so the plane is like this, right? And if you try to this epoxide from the bottom side, so from this bottom side, there will be a steric crowd because this concave plane. So the attack always takes place from the convex plane. So in this case, the epoxide of attack will be from the like this side, from this side, and therefore, so from the we are getting this exodirecting product as a major product. So here you can see attack on the least hindered phase. So this has the this downward phase was the sterically crowded, right? And this on the upward phase there is no such steric crowd comparatively. So we get the major product as a like this exodirecting, and we get the minor product this one. So this is also the example of stereo selective reaction. Okay. So We'll take few more examples on this stereoselectivity because it is very important topic that we need to you should understand at this stage only. Otherwise, when we are doing some problems on the such retrosynthesis in which involve this stereoselectivity, then you may encounter interval. So let's say a few more examples. So this is the example in which we are doing the reduction. And if you are doing the reduction with the LiLH4 and with the diol H, so this diol H is comparatively, you can see here, quite bulky compared to the lithium aluminum borohydride or lithium aluminum hydride, right? So if you look at the carbonyl center, now the hydride addition can take place either from the top side or the bottom side, right? So in this case, since the methyl is on the top side, to avoid this steric crowding, the LiAlH4 attacks takes place from the bottom side to the carbonyl group, and we are getting this hydrogen directing downward. And this product get as a major product in the Li lithium aluminum hydride because itself has some steric crowd. But if you want to increase the selectivity now, so what we can do, we can use the some more bulkier reagent like diisopropyl diisobutyl aluminum hydride. So this diol H, what it do, it creates the steric crowding, and therefore the whatever the attack takes place in case of this LAH from the top side, and we are getting about 24% of the this product. We need the hydrogen is on the top side attacking, right? But and only the 75%, which is still major, but still if we want to have the pure product, then what we can do, we can use this bulkier product in which the we can directly attack this hydride on the bottom side, and we are getting nearly 100% of this product in which this hydrogen will be here on the directing downside downward. Since here there are two chiral centers, so we call it as a diastereo selectivity here. If there is only one chiral center, then we call it as a enantioselectivity selectivity. And if you have the two chiral center, then we call it as a diastereoselectivity. So this is the difference between the stereoselectivity and stereoselectivity, and in particular stereoselectivity, enantioselectivity and diastereoselectivity. If only one chiral center is creating in the product, then it will be a enantioselectivity. If more than one chiral center is creating in the product, then it we call it as a diastereoselectivity. Anyway, so this is combined, it is an example of stereoselectivity. So we'll focus only on the stereoselectivity. Now take the another example. Now let's say if you perform the reduction reaction on the alkyne molecule, let's say this is the alkyne molecule RC triple bond C R, and we are doing the H2 palladium based reduction, and this is BaSO4 if you have added. So in this reaction condition, the reaction stop at the alkene state, not goes to the alkane. So in this alkene stage, when you perform this reaction with the H2PD and the BaSO4, so reaction stop at the alkene stage. But now if you look at the in this reaction, so we are getting the cis product as a major product when we are doing the palladium reduction. But the case we are using the Na sodium metal in the liquid ammonia. In that case, what we get? We are getting the trans product as a major product. Why? Because the mechanism, this goes by a radical pathway, and this goes by directly the concerted mechanism. This palladium uh, hydrogens goes attached to goes get supported on the palladium, and then the addition takes place. So I will just briefly explain the reduction mechanism with this palladium, that will be helpful. Palladium or the platinum, any metal complex, whenever there is such hydrogenation takes place on the alkyne. So I will explain here. So this is the alkyne, right? Alkene, alkyne, and we are performing, let's say, the hydrogenation reaction. So how this hydrogenation reaction takes place? So this is the bulk palladium metal means what it called. This is with solid, right? So what happened first? These hydrogen molecules get absorbed on this platinum or the palladium or platinum. So like this metal complex, right? And or iron nickel. So in this case, this uh, so platinum or palladium or nickel. So these are the this is the metal complex, right? So this hydrogen get supported on these, get absorbed on the this metal, and then what happen further on the same metal when it is this bond breaking takes place. So this hydrogen now these hydrogens are now attached on these metal complex by the such bonds. Now when this olefin comes in the contact with the these hydrogens, so it will form the like this coordinate bond something, and then we get the product in which you can see this new hydrogens will be on the syn side. So when you are doing reaction on the alkene, then we get the alkane in which the hydrogens are on the syn side. Now in this case, what we are doing the reduction of this alkyne, but we are using the sorry, barium sulfate. So the reaction stop at the alkene stage, and since we are using this alkyne and this palladium metal complex, so we are getting the cis product as a major product. But what happened in the liquid ammonia and the sodium metal or the lithium metal? This metal gives the electron, one electron at a time to this olefin, and therefore this reaction goes by a radical pathway, and we get the trans alkene as a major product. Sorry, yeah, so trans alkene as a major product. So the reaction pathway is different, therefore we are getting two different product. If you just look at these two reactions, so depends upon what product requirement we have, we can use the reaction condition. So this is the just general difference between the stereospecific reaction versus stereoselective reaction. So what does it say? The stereospecific reaction is a reaction in which the stereochemistry of reactant completely determined by the stereochemistry of product without any other option. So means we are getting 100% always. Also, it gives the specific product from the certain reactant. Final product depends upon the stereochemistry of reactant. This is about the stereospecific reaction. But what about the stereoselective reaction? So the selectivity, stereoselective reactions is the reaction in which there is a choice of pathway, so as I have shown earlier, but the product stereo MERS is formed due to the its reaction pathway being more favorable than the other product, one product being more favorable than the other product. Also, it can result in the multiple product. And the stereoselectivity of the reaction pathway depends upon the difference in the steric effect and the electronic effect. So it depends upon the as I have shown one example here. So you can see this example of this reduction. So, so depends upon the chiral environment of this adjacent, the stereochemistry of this chiral center is get affected in this reaction condition. So that's what happen in the stereoselective reactions. So any doubt up to this in the stereoselective and the stereospecific reactions? Now we will see the what is distereoselectivity and the distereoselective reaction and the enantioselective reaction. So these are the two examples. One is the distereoselective reaction and another is the enantioselective reaction. So a stereogenic center is introduced into the molecule in such a way that diastereoisomers are produced in unequal amount, which is in the diastereoselective reaction. But in the enantioselective reaction, a reaction that produces two enantiomers of the product in unequal amount. Unequal amount means, as I mentioned, okay, this enantiomeric excess and diastereomeric excess, we'll see that one first, so then you can know. So let's take this example. So in this example, let us say we are getting so this enantioselective reaction. So this is the simple benzaldehyde. We have used this some reagent in which you can see we are getting the two product in which this hydroxy group is upward and hydroxy group is downward. So basically this is the reduction reaction performed, and in this reduction reaction, so this hydrogen directing downward, this hydrogen directing upward in this another product, and so this is the chiral ligand they have used. So right now we are not dealing with this, not really worry about what is this chiral ligand. Now in this condition, whatever the condition given, so we are getting this product. Let's say one is the S and another is the R. So I'll just change this percentage just for easy calculation. So this one product form in the 80%, another product form in the 20%. So this another product getting formed in the 20%, right? So depends upon this A product and the B product. So now we have the two products. The first product is the A and the another product is the B product. So the A product is in 80%. So that is obviously the major product. Now the B product is the 20%. Now if we look at what is enantiomeric excess. So basically, so this product is formed in the 80%. The enantiomeric excess represent. So how to calculate this enantiomeric excess? So this 80 we need to, and this 20%. So this 60% is the enantiomeric excess. So 80 minus 20, that's the 60. This 60% is enantiomeric excess. So in this reaction, we are getting the enantiomeric excess about 60%. And diastereoic ratio is 80 and 20. So that's the the enantiomeric ratio is this 80 and the 20. This is the enantiomeric ratio, but the enantiomeric excess is 60%. Why? Because this 20%, whatever this 20%, the unwanted product, that is B product form, which cancel out the optical rotation of this uh, 20% from this measure. So basically, the 60% only we have the enantiomeric excess, and the 40% from this one, this product form is the racemic mixture. And the similar case in this diastereoselective reaction and the diastereoselective in this also. So in this reaction, this granulation across this carbonyl center, which is mainly governed by this adjacent bulkier group, adjacent groups. So in this case, if you compare this phenyl and the methyl, phenyl group is more bulkier, and therefore this incoming new phenyl, let's say this phenyl, the green phenyl, which comes from the opposite side, or the, let's say in this case, which is directing downward, this phenyl ring, this phenyl is which is from the adjacent, so directing downward. And therefore, this new incoming nucleophile attack on the from the upward side, and we are getting this as a major product and another as a minor products. So whatever the product form, the ratio of these two products are 91 and 8. 91 is to 8. So this is as a diastereoic ratio. But what is diastereoic, sorry, excess in this case? So this 91.5 minus 8.5. So this will be your in a diastereomeric excess. So how much is that? So if I just calculate that one, so 91.5 minus 8.5. So it will be 83% is enantiomeric, sorry, diastereomeric excess. So this 83% is enantiomeric excess, and diastereomeric ratio is 91.5 is to 8.5. So this is the diastereomeric ratio. This 83% is the diastereomeric excess. Any doubt in this diastereomeric ratio and diastereomeric excess, also on the enantiomeric ratio and the enantiomeric excess? We're gonna see some more some actual reactions now. So which is in our day-to-day life. So which will be very helpful. So let's say this is the one reaction, the nucleophilic addition of this carbonyl across this carbonyl center. So which is the in this case we have for this aldehyde we have the chiral center adjacent to the carbonyl center, and the product formation is mainly governed by the stereochemistry present in the starting material. So let's say we are using lithium aluminum hydride as a reducing reagent. So in this case, if you look at the chiral center which has the methyl group and the phenyl group, so this bulkier phenyl group directing downward. So if you look at which is represented here by the dotted bond. Now, when we are doing the reduction reaction, so incoming hydride will comes from the top side. Why? Because the phenyl group is directing downward. So in this case, so the attack possible from the bottom side is less. So therefore, we are getting only the 25% formation of this product, but in which the hydride attack on the bottom side, but hydride attack on the top side is measured. We are getting 75% formation of this product in which the hydride is comes from the top side. Now, in this case, if you try to look at the this diastereomeric ratio calculation, so we have one product 75%, one is 25%. So if you look at the excess uh, diastereoic excess, so this is just normal subtraction. So we have the 50% excess of this in a major enantiomer. So which represent the diastereoic excess. So if you look at here, so this is the in this reaction, the diastereomeric excess is 50%. And if you look at the diastereomeric ratio, the ratio is 75 as to 25. So that's the diastereomeric ratio. So you can have you can use this formula actually. So which is basically nothing very simple. You can directly put the do the manual calculation by instead of using the formula. So anyway, so this was about the diastereoselective reaction and the inertia selective reactions. Now we'll try to move slowly to the further more complexity. So here we have some examples of such inertia selective reaction. The first very important reactive center is the carbonyl, and we'll see how this inertia formation takes place in the carbonyl centers. So To have this, we need to have some background of these, what is the phases in the carbonyl centers. So, okay, the first thing is the nomenclatures of this prochiral centers. So in this case, the example I am showing here, which is the example of this aldehyde, this benzaldehyde. So in this benzaldehyde, so this is the planar molecule, and how we can give the nomenclature on these such molecules. So this is the trigonal carbonyl carbon, and the uh, so this is the prochiral center. As of now, it is not a chiral, but upon doing, let's say, one some reaction, it can be generated into the chiral center. Therefore, it called it as a prochiral center. So in this case, depend upon the different side of this molecule. So here you can see. So this is I have drawn this carbonyl center in a plane. So if you are viewing from this space, so how it will be, whether the if you try to give the nomenclature for this one, so this will be a rephase or the C phase. This type of nomenclatures are generally used for these type of molecules. And the if you just give the numbering to this one, so the oxygen gets the first number one, and the phenyl get the number two, and the hydrogen get the number three. So this is the rephase when we are seeing this molecule from the top side. But when we are doing the molecule from the bottom side here, so which phase it will be? It will be psi phase. So that basically, when in this case, in this one, when we are drawing a molecule in the plane, so either attack can take place from this side, or either attack we can do from this side. So that is either from the rephase or either from the psi phase. This is how we have to give the nomenclature in this one. So right now here it is a simple phenyl ring, phenyl. But when we move to the some molecule in which adjacent centers, which is chiral, that time it is mainly important. So further in this, whenever we are doing the reaction on the carbon center, this is the one example or of this attack on the carbon center is important, which is the Cramps rule. So in this case, how does the center control the direction of the attack on the this trigonal carbon? So that generally shown by this Cramps rule. So let's say whether in this case, as mentioned, on the attack can be takes place from the both side. So depending upon the adjacent groups, this attack is uh, mainly takes place. So this is the one example in which you can see this is the trigonal carbonyl center, right? Now, if you look at this adjacent carbon, which has this methyl group directing upward and the phenyl group is in the plane, obviously there will be a one hydrogen which is directing downward. So that I will just draw here directing downward. Now, when we are doing the Grignard addition reaction across this carbonyl center, so this CHO, what happen? This attack takes place. So I will just draw this. So if the attack takes place from the top side, this I gave as a attack A possibility, or the attack takes place from the bottom side, this is the B possibility. There are two possibility of attack, either top side or bottom side. So depend upon the stereochemistry of this adjacent carbonyl, so adjacent carbon atom, this attacks is mainly governed. So here you can see this phenyl is more bulkier and methyl. So we have kept this phenyl on the in the plane. And here, since this methyl and the now there was one hydrogen which I have shown the downside, the methyl is more bulkier, so therefore the hydrogen addition, sorry, the methyl addition in this case So I will take it on the some more bigger screen. So then we can explain in detail. So here we have the carbonyl center, and here we have some bulkier group which is directing upward. Let's say this phenyl. We have the methyl in the plane and the hydrogen directing downward. Now we have to attack the CH3 negative. So where this attack takes place, since this phenyl group is more bulkier compared to the, yeah. So in this case, this entire phenyl group and methyl group, CH3 group is directing downward. Phenyl group is, let's say, directing upward. Comparatively, the phenyl group is more bulkier. Therefore, the attack, preferential attack of this CH3 negative takes place from the top side. That is on from which phase in this case. So this is 1, 2, and 3. This is psi phase. When we are doing attack on the bottom side, so from the from that perspective, the opposite side or the back side phase is the re phase. So in this case, the attack takes place from the psi phase, and we are getting the product in which this methyl will be directing upward. Why? Because this attack here, this takes place from the psi phase. Right. So here in this case, this psi phase and rephase is important when we are explaining such type of trigonal systems, which is a planar. So for the from if you look at the view from the front side, so we look we can see. So this molecule, so this the front phase is psi phase, the back phase obviously on the opposite, it will be a rephase. So the psi phase attack is major. Major. And this, which attack is major and which attack is minor. So that's mainly, there are several models, which is the first one is the Cramps model, and there are some other model as well. So the Felkin N model, which is also the another model. So these models, it generally deals with the, mainly explains where the attacks of these type of nucleophiles takes place, um, on which phase when we have the attack of the such nucleophiles on the carbonyl centers. So the first model is the Cramps model. And in this Cramps model, what we have to do? So we have to write down this molecule in such a way that we need, so this carbonyl center, so this is the model you can see. So the carbonyl center, we have to write down in this manner, the that is in the plane. So whatever here, this is the plane basically. This vertical axis represent the plane. So this carbonyl group and this R group, that will be in the plane. Secondly, what we have to do, we have to draw the large group anti to the carbonyl in plane. Secondly, what we have to do, the large in plane but anti to the carbonyl, right? So carbonyl is on the top, so you can see this large group which is on the bottom. So basically we have to draw we have to draw the model in such a way that carbonyl is on the top side, that is in the plane, the large group on the anti, and now depends upon the stereochemistry given in the here. In the starting, we have to draw the small and the medium group, and the attack of this nucleophile always takes place from the attack of from the smaller side group. So I will show this with the example. So in the same example that I will take, so we'll go step by step because this is the something which is always you may see such examples in the several occasion in several exams. So here I will take one example. So what we have here, let's say we have this compound in which this is the hydrogen. One is the, let's say on the top side, we have the phenyl, and on the bottom side, we have this CH3 group, right? And if you just assign the stereochemistry of this chiral centers, which is 1, 2, and the 3. So this is 1, 2, 3, and since the this fourth priority group is in the plane, we need to do invert the stereochemistry. So here it is like for this one, the stereochemistry is, what will be the stereochemistry for this one? Yes, change to R. So this chiral center is R, right? So when we are drawing the Cramps model, so let's say, so the Cramps model is like this. We have to put the carbonyl center in the plane so that we have did. Now this hydrogen, which is again in the plane. Now, so this was on the top side, right? From the front side. Now front carbon atom, right? Now the back carbon atom, we have what we will have. We'll have the two groups directing here and one group directing here. So which is the larger group we have to keep here first on the anti to the carbonyl. So that's what we have did. This pH group we have kept anti to this carbonyl center, right? So this is the carbonyl center, carbonyl, oxygen. We have kept this phenyl anti to this carbonyl. So therefore phenyl comes here. Now we also need to keep the stereochemistry constant for the back, this chiral center, whatever the chiral center present we have. Now if I just put this methyl hydrogen here and the methyl here, what will be the stereochemistry for this backside carbon? So that will be 1, 2, 3. Yes, that will be yes, right? So it should not be like this. If I just draw like this, CH3 and hydrogen, now check the stereochemistry. Now it should be correct. So 1, 2, 3, this is R. So stereochemistry of backside carbon is now R. So this is what we have, keep the stereochemistry constant. Now do the attack of this. So if you just give the numbering, so this is the larger group, this is the medium group, and this is the small group, right? Now where the attack takes place from which side now? So if you look at, attack should be takes place from this side. And what we get now? We will get, so this will become OH. This will become, we'll draw the, better draw with these particular colors. So this will become OH. Now this will become H, and this nucleophile will be, what is nucleophile? We have the nucleophile. I will just draw the nucleophile, Nu negative. This is from the front carbon, and from the back this will be remain same, H, CH3, and this pH. This is what product we are getting in this reaction. So have you understand this Cramps model? So this is little bit complicated. I hope I am able to show how this Cramps model you can draw, right? And if you just convert this product into the final structure, how it we can convert that one. So if you just move this structure to here, so this hydrogen in the plane, this phenyl directing upward, methyl directing downward, and in this carbonyl center, what we have? We have the OH in the plane. Now, this nucleophile from the backside, and we have this hydrogen is above the plane. So like this. So this is what we are getting product in this reaction. So I hope you are able to understand this one now. Now we'll see the another model, which is the Felkin N model. So in this model, so basically you have to keep the carbonyl center in the plane, but the large group you have to keep on the horizontal plane, and then you can do the attack on the this carbonyl center. So this is the Felkin N model. So this can also gives you the product formation, which product is major, which product is minor, that you can also uh, derive from by using this Felkin N model. So let's take the some example now. So on this, based on this clamps model, so this is what you have the starting material. So these groups might be L, S, and M, depends upon this medium, small, or the large group. So when you have the nucleophile, so in this case, where the nucleophile will be, so we are trying to identify shortcuts. So where the nucleophile will looks like goes here. In this case, the nucleophile will be, so you can see here on this top side. Another problem here, which is the large group anti. So this is the mechanism you can see. So what we have did here, the larger group that taken anti to this one. So we did the bond rotation across this bond. So by keeping this chiral center as it is, we have just rotated this bond to in this direction, right? So what happens when we come from here to here? So we have just rotated this bond. We have just taken this L group to here and this group to here. So basically, we are trying to get this carbonyl and this large group on the anti-periplanar to each other, right? Now attack on the smaller side. So this is the smaller group. So that is the from the top side. So here also what we did, the attack takes place on the top side. So this R goes down on this nucleophile comes from the top side. That's what we get the major product here. So this is just like a step-by-step demonstration mechanism shown here. So in these two format. So this is you can also solve this by using such converting this into the this type of structures. By this way also you will get the same product. So whichever you feels the easy, you can go by that way. Similar for the Felkin N model. So in the Felkin N model, you have to take the large group to the 90-degree to the carbonyl. So that's what here did. And the attack of the nucleophile takes place from the group that is smaller side group. So you can, if you go just go the step by step, you can able to get the product. So basically, these are all models. Basically, go helps to assign the uh, stereo selectivity in the reactions. So that's about the today's session on the different type of stereo selectivity in the organic synthesis. What we have discussed covered in this video. So basically, we have already covered the what is the stereo specific reactions, and the examples is the SN2 reaction and the E2 elimination reactions. And also in the stereo specific reaction, we have seen the formation of diastereomer. So therefore, diastereo selectivity as diastereo specific reactions as well. So when there are more than one chiral center is creating, so that reaction is diastereo selective reactions. Further, we have seen the uh, epoxidation reactions, which is again here, which is stereo specific reactions. So only one product formation here in this type of epoxidation reaction. So that will call it as a stereo specific reactions. Now, when we are trying to understand the state of selectivity, we have discussed several problems, mainly the epoxidation on the transalkene with the MCPBA. So when we are getting the 50-50 amount, that is one measure, not anything, sorry, 50-50 amount. So that will be enantiomers of each other. So this is the racemic mixture we are getting. But when we are doing the Sharpless epoxidation, and in which you can see using this minus diacetyl tartrate, we can increase the selectivity. We are getting 98% product formation, which is the only as a measure. So only one enantiomer getting in the major amount. So this reaction we call it as a stereo selective reaction. Further, catalytic hydrogenation reactions are also a kind of stereoselective reaction. So in this case, because of the steric clouding of this methyl group, so this hydrogen addition takes place from the bottom side, right? And we have also seen the mechanism for this hydrogenation reaction, metal catalyzed hydrogenation reactions, how this mechanism goes. So because of this mechanism, we are getting diastereo selective, sorry, in this case, since earlier there was one chiral center is present, so it is diastereo selective reaction. In such systems, so in which there is a hindered phase present in the starting material, so we are getting the epoxide formation exo form, not the endo, and this is the example of the stereoselective reaction again. Further, we have seen two different reaction condition, how it gives the some stereoselectivity in the product formation. So when we are using the metal-based hydrogenation, so we are getting the syn product as a cis product as a major product. But when we are doing the sodium metal in liquid ammonia, so this reaction goes by a radical pathway, and therefore in this case we are getting the trans product as a major product. Further, the diastereoselective reactions on these cyclic ketones we have seen. So in which depends upon the bulkiness of the reagent, we can increase the stereo selectivity in the product. So in this case, since this diabal H is more bulkier, so this bulkier group, in this case, the hydrogenation, sorry, the hydride addition mainly takes place from the bottom side, because from the top side there is this bulkier methyl group. So the attack from the bottom side is preferred, and therefore we are getting nearly or the 100% formation of this product in which the hydride attack takes place from the bottom side. So this is the also example of diastereoselective reaction. And if you look at the addition of this lithium aluminum hydride on this same reaction, we are getting 76% formation of the product, which is in which hydride is attack on the downside. But along with this, we are getting some amount of the product in which the hydride attack takes place from the top side. So this is again the stereo selective reaction, but this reaction is not so stereo selective. So we need to have very selective reactions. Then we need to optimize the reagent condition as we see here. So by we can achieve the selectivity by modifying the reagent by using different reagent conditions. and the difference between stereo-specific reactions and the stereo-selective reaction, that also we have covered. So that's about the today's some fundamental concepts. Now we'll move to the actual some problem which actually involve the retrosynthetic problem, which actually involved in the stereochemistry. So let's say I have some examples for the retrosynthesis. Why this chiral uh, type of retrosynthesis is important? That we'll start doing some uh, problems on the retrosynthesis of these chiral molecules. So why it is important? So if you look at here, so this is some of the examples of the alkaloids. So important asymmetric importance of this asymmetric synthesis. So this is the L dopamine which treats the Parkinson disease. But if you look at the D dopamine, which is a toxic. So when we are trying to get the medicine, so if in our medicine, if there is another isomer is present or the stereoisomer is present, then it is a toxic to our body. So therefore, we need a very selectively this L dopamine, not the D dopamine. And when we are doing the lab scale synthesis, then we have to worry about the which stereoisomer we are getting, whether our reaction is perfect, that is, we are getting very specific product, or we are getting something side products as well along other enantiomers also along with our actual enantiomer. So this enantiomer is active one, but another enantiomer is toxic to our body. Further, if you look at the another example, so this is 25 microgram trap, thousands of bitlets, but retain 10% activity, and even 1% of this compound destroy the activity. So that's what, if you have this enantio pure compound, so in this case diastero pure, then and then only it will be useful. Otherwise, this can destroy our activity. So destroy this, uh, it will not trap these metals. Anyway, another, this is the antidepressant medicine. Sometime, uh, whatever the enantiomer, they can be fatal to, they can be toxic here. Here they have some activity, but here they can be inactive. So this is the third example in which, so this is the this S citalopram. This citalopram, this is the antidepressant, but this R citalopram is inactive. So this doesn't have any reported toxicity reported with our body, but this S citalopram uh, is only useful. So if you look at the sum of the medicines, so which has the one of the isomer is active, but another isomer is non-active. But since the another isomer doesn't have any reactivity or any activity, so we can use that one in the racemic form. But in case if some other isomer has any kind of toxic effect As in this case of this D-dopamine, then we cannot use this dopamine in the racemic form. We have to have this dopamine in the enantiomeric pure form. So therefore, this asymmetric synthesis is important. And we have seen some examples. So we have to use our synthesis stereospecific reactions for the preparation, or we have to use the uh, purification in such a way we can isolate only one of the pure required product, not the racemic. So therefore, it is important to study this asymmetric synthesis. If you look more and more example of this one is the some approaches to some more example for these chiral centers. So that I will put some, maybe today we can stop here, but maybe in the next video I will discuss that in the more detail. So how this type of isomers, only one isomer we can prepare. So there are different approaches we can get the only one isomer. Either we can work on the purification. Let's say we are getting, let's say, the racemic mixture of the two product, but but if we pure that product and we isolate that product in the reaction, from the reaction only one product, and so that time we can use that one. So that resolution or the purification is one technique. Then another technique is we can use some stereospecific reaction that we can get only one product as a major product. Or third is like some, we can use this some chiron approach, in which in the synthesis we carry forward this chiral center from the starting, not creating new chiral center. That time we can keep that chiral center constant, and that also one of the approach we can get the pure or pure product. So that can be used as a, let's say, for the drug application or any application whichever. So there are different methods uh, are used to perform such asymmetric synthesis. So that we will discuss in the next video. So does anyone have any doubt as of now? Please let me know. I will stop here for few minutes, and then we'll leave the session.